Hello again, everyone. It's Miss Fisher. Hopefully you're having a lovely day. We are going to do Unit 1, Day 3. This is exponential in logistic modeling. These are two of our 12 basic functions. So today we're going to learn about that logistic function that we saw on day 1. All right. Okay, so to begin with, let's review exponential models, which y'all talked about in Math 1 and also in Math 3. So an exponential model is going to take the form of y equals a times b to the x power. Now remember, the mother function just has a number raised to the x. So when you have other exponential functions, you can add other numbers in here through multiplication, addition, subtraction, division, things of that nature. So there are a couple of kind of rules in here when you do this. The b value must always be between 0 and 1 if you are talking about decay. And b's got to be greater than 1 if you are talking about growth. Okay, some other issues here. A cannot equal 0, because if it equals 0, then everything's just gone. And typically, if we're talking about growth and decay, A itself is not negative, but you can have a negative out in front. That just simply flips your graph upside down. All right, so that's kind of a key feature. So then let's also talk about what these different things are referred to. So if you have this number right here, the a, that is usually referred to as your initial value. And the reason that's called your initial value is because if you were to substitute in a 0 for x here, b to the 0 power would come out to 1, and 1 times a is a, and that means that when x is 0, y is a. So that would be your y-intercept, or the value of the function at the beginning point. Usually x is time, so that's what you have initially at the beginning of the problem. So that's your initial value. All right, so b here, b is typically referred to as your growth factor. That kind of determines how things grow. So like I said, if it's 0, between 0 and 1, it's decaying. If it's greater than 1, then you have growth. Okay, so basic shape of these functions. They're going to look something like this. If you have this, then that would mean you are decaying and you have a growth factor between 0 and 1. But you could have a negative a value. So this just means a is negative. That's just flipping your graph upside down. So this would still be considered decay in this situation. All right, it's just you have a reflection of your graph. So this is decay in this situation. All right, you can also have growth. Looks something like that. All right, so this is where you've got b is greater than 1. Again, you can have a reflection of this graph. The reflection just means here again that a is negative. All right, and this would be an example of growth. And then just the reflection of that. So in both of these, you have a horizontal asymptote right here at the x-axis. Okay. So, and we talked about that asymptote on day 1. All right, so we can ask you some questions about this. So as an example, I can ask, giving you an example, like y equals 3 times 4/7 to the x power, and then plus 2, something like that. And then I can ask you all kinds of things like, what is the initial amount? What is the y-intercept? Is this growth or decay? And what is the end behavior going to be? All right, so when doing this, you have to be really careful because it says initial amount. And so a lot of people just look right here and say, oh, the initial amount is 3. But no, I tried to trick you. The initial amount would be 3 if we didn't have this plus 2 at the end. So remember, we just mentioned that the initial amount happens when you substitute in a 0 for x. 4/7 raised to the 0 power is 1. So all of this becomes a 1. 1 times 3 is 3, but then you have a plus 2. So your initial amount, so the amount when time equals 0, or at the very beginning, would actually be 3 plus 2, which is 5. This also ends up being the same as your y-intercept. So your y-intercept is 0, 5. So is this growth or decay? To determine that, you need to look at your growth factor. Your growth factor is 4/7. So you look and see, is this between 0 and 1, or is it greater than 1? Since it's between 0 and 1, this is decay. For end behavior, they want to know essentially which one of these graphs up above would this be like. So since we're between 0 and 1, A is positive, it would look like the very first graph that we drew. So it would look kind of like this guy. So when we talk about end behavior, we want to know as x goes to the left, where is the y going? And as x goes to the right, where is the y going? So the way that we're going to write this answer, we're going to say the limit as x approaches infinity, that's going to the right. The f of x, which is our y, is going to that asymptote. Now, typically, on the one I highlighted in purple, that asymptote's at 0. However, in this problem, everything's shifted up 2 in the air. So our asymptote would be at 2, not at 0. So this would be approaching 2. So our graph truly would be something like this. It would be shifted up in the air too. Sorry, that was messy. So it'd be going something like this. And this point would be the point 0.05. And this would be y equals 2. To finish off end behavior, we need to talk about the limit as x goes to the left, which would be toward negative infinity. If you look at the little sketch I made, the y would be shooting straight up into the air. So that would be going to positive infinity. When we ask you these questions, it's basically just giving the reader of your answers a good idea of what is happening on the graph without necessarily having to look at a picture. Now, I drew a picture for you guys because you might not have had a good idea in your head. Our goal for this year is to get you to a point where maybe you can picture this stuff in your head. All right, another type of question that we can ask is for you to actually go ahead and make a model. So writing the equations. We can do that a couple different ways. One way is from a table. So I can give you information like x, g of x, and then just give you some numbers. Let's just do -2, -1, 0, 1, 2. And then g of x, let's do 128, 32, 8, 2, and 1/2. And then we're going to want to write a model from this table. So as you are looking at this, you want to determine what kind of pattern you see as you look at the y values. So you need to kind of decide what kind of model it is. So you need to decide a pattern as you kind of look at these y values here. So you have to think to yourself, what is happening as you go from 128 to 32, from 32 to 8, from 8 to 2, from 2 to 1/2. And hopefully, as you've looked at that, you've discovered, oh, wow, each of these is divide by 4. When you see a multiplication or division pattern like that, then it is kind of your clue that that is an exponential function. So we want to use the basic model a times b to the x power. All right, so a times b to the x, you want to then ask yourself next, what is my initial value? So again, the initial value happens when x equals 0. So that is right here sitting in front of us. So that means a is 8. Okay. Our growth factor is going to be that to get from one term to the next, we need to divide by 4. So our growth factor is 1/4. Each term is 1/4 of the term before it. And if you are unsure as to whether or not you did it right, you can substitute in numbers and make sure that you're getting the correct answer. Math. So cool. All right, another way that you can write down some equations is if you are given a graph. So, from a graph, if I give you a little picture, nice crooked picture, it'd be something like this. You would need 2 points on your graph, at least 2 points. So let's say that this is the point 0, 2, and this over here is the point 2, 6. Again, you need to assess what kind of graph you have in front of you. This looks like it's exponential because we have this lovely little horizontal asymptote right here. And it follows the basic curve of exponential. So we want to look at the model. A lot of times you're told, we'll say find an equation for the exponential shown, something like that. But again, you want to start with the initial value, which is the value when x equals 0, which is this guy right here. So you want to substitute in the 2 for a. Okay, but the problem is we don't know what the growth factor is because we don't have enough points on here to observe a pattern. So what you're going to do instead is you're going to refer to this as x and this as y, and you're going to substitute those values in right here and here. So y is 6, and oops, I erased the wrong thing. Sorry. This is still b. You're going to substitute in right here. X is 2. So then you are going to solve this for b. And to do this in red. There we go. So you're substituting in your x and your y. You are going to solve. So divide by 2. You get 3 equals b squared. Okay, so square root both sides, you get the square root of 3 equals b. So your exponential equation is y equals 2, and then square root of 3 to the x. Now it's just the square root of 3 that's raised to the x, not the 2. If you remember from math 3, a square root can also be written as 3 to the 1/2 power. So you might also see this like on an SAT or ACT. It might be written as 2 and then 3 to the 1/2 power to the x. And when you have a power to a power like that, you multiply the powers. So it might be written like this. 3 to the x over 2 like that. So you might see it like this on a multiple choice question, or you might have it like this. You need to kind of be familiar with both. All right. The last thing that we are going to talk about in our notes, and then we'll practice in class, is the logistic. Okay, you saw the parent function of this on day 1. All right, it looks a little bit more complicated as soon as you start to add other numbers into it and do some shifting, okay? So essentially this is used as a more realistic growth model. All right, as you look at the exponential model, notice up in like this last example where you make an exponential function, if it's exponential growth, it just grows up to infinity. And that's not realistic in life. You can't have a population that grows to infinity. And I think you talked about that in some of your humanities classes. Populations can't grow forever. We run out of resources like land, water, things like that. And so usually what happens is things like natural selection happen, viruses come and kill some people off. It's kind of morbid, but that's what happens. So this is a more realistic way to model the things that happen. And so this is what we end up getting. So we get y equals c divided by 1 plus a times b to the x is one version of it. The other version is y equals c divided by 1 plus a e to the negative kx. Okay, so in both of these, the c here at the top, that's the carrying capacity. So that is basically how much the space can hold. All right, so okay, due to resources and things like that. You can't have more than a certain population. So because of carrying capacity, pardon me, because of that, the model ends up looking like this. Sorry guys, I have a cold. My students know that. I've been sick for a couple weeks. Just fast forward through this part. All right, so this is the only one that has two horizontal asymptotes. The first one is at the carrying capacity. The second one is at the horizontal asymptote of y equals 0. Okay, so that's essentially what it looks like. It doesn't matter which of the equations you use if you're trying to write your own equation. One has e in it. That's the natural number e. That's how things grow in nature. So that's how like viruses spread. That's how bacteria grows. We talked about that in Math 3. If you have more questions on that, ask your teacher in class, please. All right, so let's just look at an example. So we'll say the zombie apocalypse. I should have thought this through. I don't think I know how to spell apocalypse off the top of my head. We'll just call it apoc. The zombie apocalypse has hit Broughton. And the number of students who turn into zombies can be modeled by P of t equals $2,100 divided by 1 plus $9.99 e to the negative 0.5 t, where t is time in days. All right, and then we can ask you some questions. So some favorite questions to be asked would be, what is the maximum number of zombies at Broughton? What do y'all think? Maximum number of zombies at Broughton. Hopefully you said 2,100. That is a carrying capacity, so you cannot get any more than that. So that is not meant to be a trick question. That is just wondering if you know about the carrying capacity being the top limit. You cannot go higher than that. Okay, so carrying capacity is going to be your maximum number. Okay. All right, how many zombies are there at Broughton initially? Okay, so that looks like an initial value question, which it basically is. The thing you got to be really careful about here is that a lot of people look at this $9.99 and they think, ooh, the answer is 999 because that's an A value. But that is wrong. Remember, initial value is how many are there when you have the initial time. So you need to substitute in t equals 0. So that's really 2100 divided by 1 plus 999, and then e to the negative 0.5 times 0. So again, you've got 0 up here. E to the 0 power is just a 1, so that's all a 1. So you've got 999 times 1, which is 999, plus 1 is 1,000. Okay, so you've got 21 divided by 10. So roughly 2 students. You have about 2 zombies initially. Okay. 2 zombies initially. Then we can ask different things like how long will it take to have 700 zombies? Okay, so a question like that, you'll want to go to your calculator and put P of T in Y1 and put 700 in Y2 and find the intersection. All right, and so we can go over that more in class. I can't really show you that here because I don't have a calculator to display for you. So we're going to go ahead and end there. Hope you have thoroughly enjoyed this lesson. But we are done. Bye.